All right. Welcome back, everybody, to Complex Differential Geometry, where we're still in Lecture 4. This is Part 3, and this hopefully will be the last part of Part 4. So we were looking at vector bundles. So today we're going to be looking at a specific type of vector bundle called a tensor bundle. And before we get into tensor bundles, let's do a brief recap of what we were doing before. So number 1, we looked at vector bundles. We defined what a vector bundle was. It was this triple EM pi. We did a more in-depth breakdown of the synopsis of the last few lectures in the last recording, so you can look at that if you want. But I'll go over this in a much more high-level way. So the second thing that we did was we looked at global sections. So global sections were these maps S from M to E on the manifold, and then we also looked at local sections. So these were the same maps, but we restricted them to an open set U alpha subset of M. So we took a set of these local sections, and then we constructed these things called local frame fields. Which were the sets L is equal to a set S alpha, where alpha is equal to 1 to Q. And this represents a choice of a Q-dimensional basis for the fibers within U alpha. So that's what we did, and then we looked at a specific example of that. That was the tetrad formalism. Which was a 4-dimensional local frame field on space-time. Then, in part 2, we looked at a particularly long theorem that said that there exists a vector bundle on M, and it's unique. If you have these maps G alpha beta that go from the intersection of two open sets U alpha and U beta to the space of linear transformations on F, where F is the fiber. And so if I take, let's say, G alpha beta of P, then I get a single linear map. And this is the linear map that tells me how to go from the, so let's say I have a fiber FP on this point P. It tells me how to go from the representation of FP on a U alpha to the representation of FP on U beta. And if this has the if this has the property that G alpha alpha of P is equal to the identity of FP to FP, and the three-way round trip, so G alpha beta of P after G beta gamma of P is equal to G alpha gamma of P. If these two are true, then this will always be true. So that's what we proved. It was a pretty long proof. The way we proved it is that we constructed em pi, then we constructed these maps phi alpha, from which we constructed, so we started with q, and then we went to phi alpha, and then we went to phi alpha p, and then we used the phi alpha p to construct this set g alpha beta. And without this g alpha beta, if you go back to our definition of what a vector bundle is, without this thing will not be a vector bundle. So that's how we proved that it was a vector bundle. And right, so there were lots of steps in proving that all of these things were continuous, because this had to be a set of continuous maps. And here we are. So now we're ready to look at these things called tensor bundles. But in order to talk about tensor bundles, we have to talk about tensors. And tensors are examples of vectors. Vectors in the sense of vector spaces. Okay, so we're gonna first look at tensor spaces. Tensors and tensor spaces. So a tensor, let's call it TP, it's also associated, for our purposes, a tensor is associated with a point on the manifold, just like a vector is. So because this is essentially what's going to be an element of our fiber, and so this is, well, let me draw it out first. So we have these product, oh, this should be a Cartesian product, sorry. So v star times v times dot 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 times v goes to c. In our case it's c, because we're doing our geometry on complex spaces. So there should be r of these and s of these, and so in general, let's say that this is just a general tensor T. A general tensor T is something called a multilinear map. A multilinear map, which means that it's a map that is linear in any of its entries. And so like the general property of linearity that you expect from a vector space, so we'll have a map that looks like this: alpha, beta, gamma, and it'll be linear in each of its inputs. So that kind of looks like this: alpha, let's say that c1 beta 1 plus c2 beta 2, gamma, let's say that this is a tensor that takes 3 inputs. So this will be equal to c1 t alpha beta 1 gamma plus c2 t of alpha beta 2 gamma. And it'll work for any other of the inputs. So alpha and gamma work the same way. So that's what a multilinear map is. And so in order to talk about we are interested in a very specific type of tensor. So that's where I'll bring back this notation TP. We're going to think of, so these are vector spaces. And this is the dual to that specific vector space. So it's a multilinear map that specifically maps R covectors and S vectors. So we're going to specifically look at the types of tensors that work on V equals TPM. So V equals TPM, what does that mean? That means that we get TP star M, which is the dual to TPM. And so what it does is that it takes R covectors and S vectors and maps them to C. And so, yeah, so there are R of these, and there are S of these. And so this is called an RS tensor, where R is called the contravariant rank, and S is called the covariant rank. I think they're also sometimes called the order. And so there's also something called the overall rank, and that is R plus S. So all the tensors where R plus S is the same are the same rank tensor. You could have, for example, you have the 2, 0 tensor, the 1, 1 tensor, and the 0, 2 tensor. And that tells you how many of each of these inputs it's going to take. 2, 0 tensor takes 2 covectors, whereas the 1, 1 tensor takes 1 covector and 1 vector, or contravector. So I'm going to try to use the word contravectors to not get confused with general vector spaces, because contravectors are specific kinds of vectors. So the elements of these are called covectors, and the elements of these are called contravectors. And that's because of the way that they transform, but we don't have time to go into their transformation properties. That's for a course in tensor algebra. But suffice it to say, these are all rank 2 tensors. Rank 2 tensors. So before we continue, I think it'd be a good idea to talk about what exactly this going to C means. So I think something you'll hear a lot informally in describing tensors is that tensors are maps that eat vectors and covectors. And you could see that here. These input covectors and vectors are what the tensor eats. But we know that, let's say we have a covector omega p, then we know that it's a map that takes a vector and spits out a scalar, right? In this case, a complex scalar. So, but can we really think of a vector as a function that takes so this is by the way what we mean when we say it eats a vector. A covector eats a vector. This might be very physics brained, but I think of vectors and covectors as particles and antiparticles. When they come together, they annihilate, and when they annihilate, they produce a member of the field. So just like how a covector can eat a vector to produce a complex number, a vector can also be thought of as something that maps something from TP star M to C, and so it would eat a covector and spit out a scalar. Now that's not clear from the way that we define vectors. We define vectors by saying that, okay, well, think about this specific curve, gamma, p, and then take t equals to 0, and then we'll associate that with some vector vp, right? And then we took this equivalence class of stuff like that, stuff of this nature, and then we said that, okay, well, that representative of this equivalence class is a vector, right? But we can think of that's because we thought of vectors as the fundamental objects, and we thought of covectors as the duals to vectors, that they are linear maps that take a vector and then produce a complex number. But in fact, if we took the dual of the dual space TPM star, if we took the dual again, then this space is actually isomorphic to TPM. we can, I'm gonna do a loose proof of this fact. So firstly, we would need to find this isomorphism. The way you can think of this isomorphism is that, call this isomorphism phi. So then we go from this isomorphism phi maps something in TPM to something in TPM star. I'm gonna have a tough time pronouncing this. TP star M star. And the way it does that is, the way we map it is that we have phi of v. This is a map now. Once we apply phi on v, it becomes a map. And then we use that map on this covector omega p. Let me make sure to put p subscript on everything. So this is defined to be the same thing as the covector acting on the vector. If we define it this way, then we have a valid isomorphism. You can loosely, we're going to do it loosely, but you can prove that this is injective, because the kernel of this map, the kernel of phi, is equal to the 0 set, or the set containing the 0 vector. If it weren't, if it didn't contain only the 0 vector, then we would have a linear functional omega, well, omega p, that also mapped every VP to 0. But we know from linear algebra that the only member of the vector space that can do that is the 0 vector. So by contradiction, phi must be an injective map. If the kernel, there is a proof that, or there's a result that if the kernel of a map is just the 0 vector, then then that map must be an injective map. Okay, so right. So then we have to prove that it's surjective, and it's surjective because every injective map between a vector space and a vector space of the same dimension, and these are two vector spaces of the same dimension. So then these are always isomorphism. So this means that it's also surjective, and therefore we skip the part where we prove that it's surjective. We directly say that, well, this has to be bijective because they're both vector spaces. This is from another result in linear algebra. So that means that this is what we call this the canonical isomorphism between TPM and TP star M star. And so that means that we can think of every VP. This is an abuse of notation. Basically what we're doing is we're associating VP with phi of VP, and phi of VP is a map that takes omega p to a complex number. So this is the way so if we were to equivocate these, or like let's just say that they're equivalent, then we get these maps. So that's the sense in which a vector is also an object that eats a covector and produces a number. So if we now think of this, so then there's this interesting way that you can reformulate what a tensor is that seems to be like a more intuitive or a more kind of satisfying explanation. So we're going to transition over to that. But in order to talk about that, we're going to need to talk about this thing called a tensor product. Tensor product of elements. So a tensor product is a specific kind of product on vectors and covectors that we can use to create higher order tensors. So remember how we had like 2 0 tensors and 1 1 tensors and 0 2 tensors. So this kind of gives us a hint as to how we're supposed to construct these tensors, because when we had our copies of TP star m, we put that as the contravariant rank, right? That should have been at least a little strange, because TP star m are covariant. But that's because we're kind of thinking about the dual formulation, where we're thinking of what is eating this TP star m, or this element of TP star m. That's the thing that's contravariant. So each of these omega p's that are coming from TP star m are being eaten by a contravariant object. That's why this is called the contravariant rank. So we're going to be able to systematically build up these tensors from taking the product of this specific product of vectors and covectors. So how do we actually define this? The way we define it is that, let's say that we have VP, which is a vector, tensor product, so that circle crosses the tensor product, with WP, which is another vector. Then this becomes a vector. So a vector, a contravector, in the sense that it will now eat two covectors. And how do we define how it eats these two covectors? We will say that it's VP of, or alpha P of VP times, in fact, we don't need to do that. We already defined the vectors as being maps on covectors, right? So we can do this, because this is actually secretly just phi of VP of alpha P. That's what we're saying. So multiplied by WP of beta P, right? So this whole thing is a complex number, right? Because this is a complex number and this is a complex number, and the multiplication obviously is also a complex number. But this is also, because this is defined to be alpha P of VP, this is actually also equal to alpha P of VP times beta P of VP. But remember that this is also how we define the inner product. So this is actually also equal to VP alpha P dot, I put VP here again, WP beta P. So that's how we're defining this tensor product. So this is how we make a bilinear map. So this is a bilinear map. This lives in this space. L for linear, V, well, in this case it would be TPM, over the field C. That's where this lives. And this is also called, so let's just introduce this here. So this is what we call, by definition, VTP or TPM times TPM. So this is, so we were talking about the tensor product of elements. That's what this is. Let me color code them so that we can differentiate them. This pink product is the tensor product on the elements in the space, and this let's make it blue, I guess. So this will be the tensor product on spaces. So these are both spaces. So this is the tensor product of the two spaces, and the way this space is defined is that, well, you can think of them as this, but you can also think of them as the result of taking all products of this sort and then putting them in a set. So if VP and WP are elements of TPM, then TPM blue tensor product TPM is the set of all VP pink tensor product WP. That's how we define this. And similarly with covectors. So if we took one of these to be a covector, then we would just get something else. So we have if we do like alpha p cross beta p, then we would take two inputs of vectors, WP, VP, and WP, and it would be defined similarly, and we could mix them too. Alpha p, so these are both the pink tensors, and so yeah, you could do something like this. So then the first one you would need to take a vector, and then the second slot you would need to take a covector. And that's how you would take these, and these would both map to complex numbers. So we can reformulate our tensor TP as being TPM tensor ... tensor TPM, where these are the blue ones. I might not want to switch the colors so often, but let me just color them all in first of all. Yeah. So, and then we get TP star M ... TP star M. So here's where, so these are there are of these, and there are S of these, right? And let me put forward or let me rewrite the previous definition that we had. So TP star M, this is the Cartesian product. The Cartesian product, as a refresher, just means that we will just put them next to each other with no other structure. Right. So TPM times right. So here we go. So and then there are of these, and there are S of these. So what gives? Why is there TPM on one and TP star M on the other, and they're flipped, right? So it's what we've been alluding to so far. So these tell you what the inputs are. Here, we're specifying the multilinear map. Multilinear map. Here we're talking about the inputs of the map. And here, we're kind of thinking of the map as being made up of these smaller maps. Each of these maps is like made up of smaller maps. And each of those maps is a linear map. This is a linear map, and this is a linear map. And so each of those maps eats one of these inputs. So each of these eats one of these inputs. So they're kind of the same thing in disguise. They're both describing multilinear maps, but they're secretly like they're two different formulations of what secretly is the same thing. Okay, so now that we've described what a tensor is, let me just check that we didn't miss anything. Yeah, I think we're good. We talked about the difference between tensor products of elements and tensor products of spaces. Yeah, and then we talked about what the relationship is between the two types of definitions. So let's now define what a tensor space is. And this is like very much analogous to the way we defined tangent vector spaces and cotangent vector spaces, right? Because you can think of tensor spaces as using tangent spaces and cotangent spaces as building blocks, building higher order, more complicated object. So we take two different types of linear maps and we compose them together to make these larger multilinear maps, right? So these are you could think of this as like a more complicated version of what we were doing with the tangent spaces in the first place. So what did we do with the tangent spaces? We said that okay, VP is this like d gamma p dt at t equals 0, or like a representative of that. Over tilde. This is not standard notation, just trying to get an idea across. So then if we take this, all of these elements, then we get this set, right? If we do VP, where VP is defined to be something like that, gamma p dt. Let me do it correctly here. T equals 0, where gamma p is an element of this equivalence class. That's what we did, right? That's how we defined TPM. So we defined TPM as the set of all unique tangent vectors. So similarly, we're going to define, the notation is going to be a little different here. So we're going to say TRS is the space of all of these TPs, where TP is a multilinear map. So let me not write it in that long way. Let's write it like this: R equals 1, or sorry, how do I want to write this? I equals 1 to R of TP TPM tensor. So I'm just using a kind of like more compact notation here, but we're writing the same thing. J equals 1 to S of TP star M to C. So that is the tensor space. We should restrict it to P. Let me bring that a little bit to the side, make it easier to read. So right. So this is what we call the tensor space. So we haven't been drawing much diagrams recently, so let me draw a diagram. So let's say that this is an open set U alpha on our manifold M, just not because we need the open set, but just because this is a subset of our manifold. So let's think of this point P. So we knew that there was this tangent space, right? There was a TPM that's attached to this P, and there's also, I'm going to draw it a little bit rotated, there's also a dual space TP star M. And so using these two spaces, we can use the tensor product to make multilinear maps out of them. And if we do that, we get this we get these higher spaces, which, let me erase that now. And so then we get these spaces of TRSP. And we get one for, so R and S can be any element of the natural numbers. That's the idea. So this isn't just one space. There's like a tensor space for every R and every S above. I mean, I don't know if you want to include 0 in the natural numbers. That's up to you. But like, yeah, going up from 0. So R and S are both greater than or equal to 0. So you get one. So there are infinitely many, countably infinite number of these tensor spaces at every point. And so now let's come to this idea of a bundle. So this is going to be our fiber. This is the fiber. This is a vector space. It's the vector space of multilinear maps. Oh, it's not a fiber space, it's just a fiber. It's a fiber at P. So this idea of bundles was always just this idea that if we take all the fibers and then we aggregate them together, then we get a bundle. And so this, so the way that we can think about this is that we call this space TRS. We no longer restrict it to P. So then TRS is equal to the union of P element of M of TRS P. So if we take every one of the similar, so if the rank is the same, so if we have RS tensors, then we get the RS tensor bundle. And that's how we're going to define the tangent and cotangent bundles. I mean, the idea of the tangent and the cotangent bundles should be obvious to us, but the reason I held off on defining them was because now is a really nice time to kind of very easily get a definition of the tangent and cotangent bundles, because of an interesting thing, which is that the tangent space TPM, if you think about it, let's say that I take T10, right? What's T10? T10, in terms of the first definition, it takes TP star M, one copy of TP star M. So like this is R, so R equals 1, so we take one copy of TP star M and we take 0 copies of TPM. So it's a map that goes from TP star M to C. So now it's obvious what this is. This is contravector, right? It's a contravector because VP is, we're saying it's equivalent to phi of VP. And this is a map that goes from TP star M to C. So, so that means that this is the space of 1, 0 tensors. 1, 0 tensors. Similarly, if we think of T01, we take 0 copies of TPM, or TP star M, and we take 1 copy of TPM. So that is a map from TPM to C, which is exactly what TP star M is. So this is that. And so this is the space of 0, 1 tensors. And so we get the idea of what a bundle is for the tangent space and the cotangent space kind of for free. TPM is so TPM is the same thing as T10 at P, and TP star M is the same thing as T01 at P. And so we're going to define, this is a special symbol, this doesn't follow the nomenclature that we've been doing so far. We're going to define the space TM. This is TPM, but without the specification of the point P at which we're looking at. So this is the aggregation over all the points P. So this is equal to T01, which is also the same thing. Well, let's say this is isomorphic to this, and this is isomorphic to if we took the union P element of M of TPM. And similarly, we can do T star M, which is T, wait, I called this 0, 1. This should be 1, 0. And so this is 0, 1. And so then this is the union of P element of M, TP star M. Okay, so this is called, there are a lot of curved arrows. Let me erase those. So this thing is called the tangent vector bundle. Tangent vector bundle. And this is called the cotangent vector bundle. And the sections of these vector bundles are quite special. If we take the section of sections, so I am not clear on this point. If anyone would like to clarify or elaborate in the Discord server, that'd be great. It seems like some people require these sections to be smooth and some people don't require the sections to be smooth. I am not sure whether this following definition requires these sections to be smooth, but let's just say smooth. Smooth sections on TM. So if we took a tangent vector at every point, as we've alluded to in part 1 of this lecture 4, this is called a tangent vector field. Tangent vector field. And if we take the same thing on T star M, well, you would think that you would get a cotangent vector field. This is more commonly called a cotangent field, or sorry, a covector field. But it seems like the most common name for this the thing that's stuck is that this is a one form. I like the name cotangent vector field because it shows the symmetry between these two things, but I'm pretty sure the reason this thing is called a one form is because it takes one element of TPM and then annihilates it into a scalar. So that's I think where idea of form came from. It could also be related to what we're going to talk about next, which is exterior forms, in which case a form is this is a sneak peek into what we're going to talk about next, but an alternating tensor. And these are the sections on Tm and T star M. These are going to be very useful for us in the coming lectures, because we're going to talk about connections, and we're going to talk about bundles, and connections are going to be defined on bundles. So we're going to use a lot of these, and so this concludes our foray into tangent bundles and their sections. And so before I want to conclude one last thing, which is not all vector bundles are tensor bundles. So if we think about vectors, there are lots of different kinds of vectors, but two important kinds of vectors are, so there definitely are tensors. Tensors are one way that you can compose these tangent vectors and cotangent vectors and then form these higher order objects. But you can also form vectors in other ways, and a very famous kind of vector that's not a tensor. I mean, in fact, a lot of people bring up spinors as being not tensors, but they're still vectors. And these, so far we've been taking this to be our fiber. If we took spinors to be our fiber, then we get something called, if this is our fiber, then we get something called a spinor bundle, or a spin bundle. Yeah, it's called a spin bundle. These are called tensor bundles. We're not really going to be talking about spin bundles. Their fibers are spinor spaces. you can investigate them on your own if you're curious. I just wanted to highlight that there are other kind of bundles, because I didn't want to give the impression that vector bundles were the or tensor bundles were the only kind of bundles, just because those were the only ones we were talking about. The tensor bundles are not the only way you can extend the idea of vector bundles. So, right, that is something to think about. Summary. We defined tensor spaces. We defined tensor products. And then we defined tensor bundles. And we looked at two important tensor bundles, which is the tangent bundle and the cotangent bundle. Right, so next time we will look at exterior algebras. In fact, this exterior algebras, if we talked about tensor algebras today, we could have talked about exterior algebras today too. They're kind of part of tensors, but given that I haven't prepared the notes yet, I'm going to elect to have them as part of the discussion of cohomology, but they go pretty well as part of the discussion on cohomology as well, because that's where we're going to start talking about forms, and cohomology kind of works on forms. So we're going to talk about exterior algebras and differential forms, and cohomology. So, and specifically, we're going to look at the Dolbeault, let's see if I can spell this right, Dolbeault cohomology group. All right, so that's what we're going to do next time. I think we're going to take like a week break, and then we're going to come back this following, it's Thursday now, so maybe we'll come back in the following Sunday. So we're going to skip next Sunday and next Thursday, and then we're going to come back on Sunday. What date would that be? The 21st, so the one after the 14th. So we're going to come back on the 21st. All right, so that's it for tensor bundles. See you next time when we're going to talk about differential forms and cohomology. Goodbye, everybody.